Hey everyone, welcome to QualQuest. I'm going to try and do 3 problems today, so let's get started. We have a finite dimensional polynomial up to order m, or next to the m, I suppose. That makes more sense. We're given the operator d just to be the derivative function, and we're asked to find the eigenvalues and eigenvectors. That's just a shorthand abbreviation of our operator. So that means we want to find particular polynomials and constants lambda, such that when we take the derivative of those polynomials, it's the same thing as multiplying that original polynomial times that constant lambda. So let's see what we can find. So this one's not too bad. Basically, we just have to take our term-by-term differentiation, try and match up our terms. So if we take the derivative on the left side, we'll have a1 as a constant, which we have to match up with lambda a naught on the right side. So matching up our powers together, we get 2a2 equals lambda a1, 3a3 equals lambda a2, etc., all the way down to our last term, where we have m times lambda am has to equal a to the m minus 1 times lambda. But when we take our derivatives, there is no x to the m term over on this side anymore, and yet there's still one over here. So then we need lambda times a sub m to equal 0. So for here, there's two possibilities. Either lambda is 0, in which case, if lambda is 0, then all of these things go to 0. So a1 is 0 and everything else. So the only thing that we don't have a constraint on is a0, which is our constant function. So if our original function is a constant to begin with, 0 times that is 0, and its derivative is 0. So that's good. The other possible combination is that a of m is 0, but then am minus 1 is 0, and am minus 2 is 0, and basically that they're all 0. But that's not exciting. So we don't really care about that one. So the important one is that our constant function has eigenvalue of 0. So here's the second part to our question. We're given some t greater than 0. We want to show that the operation e to the td times our polynomial p of x basically shifts our polynomial over by a certain value of t. So again, it's like e to the t derivative. How do you do that? Basically, you just expand it out like you would before. You know, we have 1 plus td squared over 2 plus etc., etc. And then, of course, we're operating this on our p of x. Obviously, since we have our finite polynomial of up to degree m, once we take any more derivatives past m, or any m plus 1 or more derivatives, basically those are all going to be 0. So the only ones we have to care about are the first m terms of e to the td. So where do we go from here? So let's just pick one of our powers, x to the n less than m. If we perform our operations on this variable x to the n, so we'll have x to the n plus t times its derivative plus t squared over 2 second derivative up to its nth derivative, because afterwards it would be 0. So we calculate all these things out. We get x to the n from the first term. We pull out n times t and x to the n minus 1. For the second derivative, we pull n minus 1 to the n minus 2, and etc., etc. You keep doing that with your terms until you get to the nth derivative, which in this case will just be n times n minus 1 times n minus 2 times n minus 3, etc., all the way down to 1, or the same thing as n factorial. So our n factorials will disappear, and basically we have these linear combinations of powers of x and powers of t, which may or may not look familiar. So the easiest way that I noted this out is that if you can write it as this summation, where nj is basically your combinatorics, version where you have like n factorial over j factorial, n minus j factorial, which you may or may not recognize as the nth row of the Pascal's triangle. You know, where you have like 1, 4, 6, 4, 1, 1, 5, 10, 10, 5, 1, etc. And this can also be used to represent the coefficients of the expansion of x plus 2 to the n. So since we showed that it worked for one case where we do our operation on x to the n and we get our shift by t, then we know that that'll work for all of our bases values in our polynomial. So there we go. So let's continue with polynomials, and this is the one that I talked about yesterday. Basically, we have again a finite dimensional polynomial. We're given this additional restraint that the sums of the squares of the coefficients is 1. So what we want to show is that the integral from 0 to 1 of the absolute value of our polynomial is less than pi over 2. I mean, we know that these are going to be roughly pretty small values, but let's see where this goes. Hopefully you guys can see this. Basically, if we take the absolute value of our polynomial, we have that, everything is inside this absolute value. We actually know for sure that this is less than the individual components. So we can break this absolute value up into all the different terms. This is also known as Minkowski's theorem. Basically, yeah, so we know that it's definitely less than all these things. All of these terms we can integrate by hand. And since we're just going from 0 to 1, whenever we have a polynomial, x, it just goes x to the n plus 1 over n plus 1. From 0 to 1, goes away to 0, and that value weighted to 1 is just 1. So, rewriting these terms, we have a0 plus a1 over 2 plus a2 over 3, etc., up to our am over n plus 1. And again, we need the absolute values because they could be negative theoretically. But since we're looking for the absolute value, we can just assume that they're all positive from now on. And we rewrite it as this sum, which will help us in terms of writing our solutions. I mentioned I was going to try and do my bad solution, but for time purposes, I'm going to show 2 good solutions. For our first easy solution, let's just revisit our Holder's inequality, which we used in a problem a little while ago. For this case, we're going to use p and q to both be 2, because 1 over p plus 1 over q is 1/2 plus 1/2 is 1. So we take the 2 norm of each part, so we have a1 to the 2 norm, and then we have the sum of 1 over I plus 1, those individually squared. But we were told at the beginning that the 2 norm of our that the sum of our squares of our coefficients was 1. So that's covered. It just so happens that the sum of 1 over n squared from 1 to infinity is pi squared over 6. Just take it as fact. It's just one of those things that we learned over the course of the year. So basically, our original sum, is less than the square root of pi over 6, since we have only a finite sum, so it's definitely less than that infinite sum. So it's less than pi over root 6, which is definitely less than pi over 2. Cool. Now I'll do the other version. So here's the last version that I'm going to talk about. Basically, we have 2 functions. We have our sum, which we want to maximize, and we have our constraint function g, which I just said, the sum of the square to the minus 1, just so that g is equivalent to 0. There's a thing called the Lagrant Multiplier. Basically, we want to look for the angle or the vector in which we have the maximum growth. Where basically we have gradient of f is lambda times gradient of g, where lambda is some constant. Again. So basically what that means is that we have to take the partials of both f and g with respect to each individual variable in order to figure out what that value is. So taking the derivative of both sides with respect to a naught, we just get 1 for f and 2 a naught lambda for g. So then lambda is just 1 over 2 a naught. That's okay, but what is a naught? We don't know yet. Doing the same thing for a1 over 2, the derivative of that with respect to a1 is just 1/2, and again we get 2a1 lambda on the right side. So lambda is also 1 over 4a1, and then same thing, 1 over 6a2. What this means is that we can rewrite our a1, a2, and a3, etc. in terms of our a0. So a1, just rearranging these terms, is a0 over 2, a2 is a0 over 3, etc. So now we have a0 plus a0 over 2 plus a0 over 3 etc. So the other thing to remember is that the sum of our squares is 1. So bringing that out, we can factor out the a0 squared now, and we just have our 1 over sum of n squared again. So again, this is a finite sum, so it's not quite our pi squared over 6 yet. But that tells us that our a naught should then be 1 over the square root of the sum of our squares. Which is useful, because then going back to our original sum notation, we have a naught times the sum of our squares. So we have 1 over the square root of our sums of our squares times the sum of our squares. We get a root that cancels out. We have the square root of the sum of 1 over n squared, which again, the inside part in infinity would go to pi squared over 6, take the square root, and we have the same inequality as before. So this is useful for more nonlinear equations, but it also worked in this case. Okay, I'm going to try and do one more problem, time permitting. So since the other two problems were methods and an analysis, I figured I would finish off with a numerical question. We're given this weird update scheme where we take the previous point, the derivative of that point, and the derivative at the previous point to try and find an estimate for our next evaluation point, with using a step size h. So what we want to find is the point on the boundary of absolute stability, I forgot to write that there, where we have the most negative real part. Basically what that means is that for these complex iteration schemes, we can have regions of stability that that go across the complex plane. So, maybe it could be just a little circular path, in which case we would just look for the leftmost part with real. Or it could also be a really weird convoluted path of stability. So again, we need to try and find that region where it's most negative. So how do we do that? So the region of absolute stability, it's defined by this weird function, rho of z over sigma of z, where rho and sigma are polynomials based on the coefficients up here. It's a little complicated to explain, but basically take the earliest term and set that as your base, and then for the next term you would have like a z power, for n plus 1 you would have a z squared power, etc. So, and then you just include the coefficients that are in the front here. So rho z depends on our yn terms, so we'll have z squared minus z, since we don't have an n minus 1 term. And then sigma will be 3/2 z minus 1/2. So in order to find this region of stability, we let z equal e to the I theta. That way we can vary theta and we can exactly know where our boundary is. So now our question is to find the most negative part, or most real negative part of this nasty thing. So I'm going to do some nasty algebra, and I'll get back to you on that. And there's my work so far. Okay, bye. Alright, so doing just a lot more algebra. Basically, you combine all our terms, do some nice substitutions, like sine squared is 1 minus cosine squared. And we get this thing. We have cosine theta minus 1, quantity squared, negative of that, over 5/2 minus 3/2 cosine theta. And again, that's the real part, so that's the only part we care about. So, to find the minimum, or, you could either try and take the derivative where it equals 0, or just kind of intuitively look at it. We know that the denominator is going to be positive for all theta, because 3/2 is less than 5/2, so the denominator is always going to be positive. So then we would want to make this numerator as negative as possible, and so that's going to happen when theta is pi, so that the cosine is minus 1. So we're going to have minus 1 squared on the inside, so we'll have minus 4. Cosine of pi is minus 1, minus 4 over 4 is minus 1. And I'll actually show a picture of that. I'll attach that right now. Boom. Hopefully that worked. Hopefully you can see that that's actually where the minimum is in the region of absolute stability. So, this is Big Mac saying later for the last time from QualQuest. See ya.